So let's do questions and answers. And let me see. Mr. Murad again. Okay.
Hey, Todd, can you hear me?
Hey, Paul. Yeah.
Great conversation. Let me ask you one question. Your damping factors are usually values less than 1. What would ever happen if the damping factor was imaginary, an imaginary number?
If the damping factor were an imaginary number, I don't know how to do that. That would be essentially.
It's when your B factor gets bigger than your B0. Let's say.
Yeah, I don't have an answer for that. I don't know what would happen. I don't know that it's possible.
Okay. That's acceptable questions. Answer.
Yeah.
Okay, well, thank you, Paul. Let me see, and who else would like to go? Does anyone else have any questions for Todd? Oh, and there's Wayne. Okay.
If anyone in the chat room has questions, all caps for anyone in the live chat.
Hi, Todd. That was a great explanation. I was just wondering if you could comment on how the Earth would generate the gravity field, or how that interaction might,
like I was saying, in a vacuum far from the Earth, right, far from any other matter, then we have an entanglement that is very coherent, and the coherence is a resonance, in that atomic state. And when you're at resonance, you've got your maximum inflation up to the point where the 0 point field is going to inflate that particle until it reaches the limit set by the damping factor. So the Earth is a conglomeration of uncountable number of particles that are all radiating electromagnetic fields, and all kinds of particles. So we're bathed in a particle soup right now, and the probability distributions of all those atoms and particles surround us. So their interference, they're a destructive interference that acts on that resonance that causes it to collapse, and as it's collapsing, it falls. It increases the resistance.
Okay, that's good. Thank you.
I wanted to mention, Tim, about some of the experiments I'm trying here. Behind me in this picture is my little new lab bench I set up. And essentially, I am trying to make my own little nuclear magnetic resonance experiment here. And I've tried a few things, but I can't generate a sufficiently uniform magnetic field and with a large enough sample. So I have ordered some more toys to play with, some very large inductor coils, air core inductors, some pair of Helmholtz coils, and some more equipment that I'll be able to use to generate an NMR signal. Once I have this NMR signal in a sample tube, I should be able to generate with a gradient coil a gradient field where I can physically show on an oscilloscope that the resonance frequency changes in one direction up and the other direction down. And then I can weigh a sample in this field and show that the weight increases or the weight decreases due to this force that I was talking about.
Okay. Paul?
In 2001 and 2002, I got very heavily involved with a Russian scientist named Dyatlov, who felt that Shipov's physical vacuum, which was homogeneous, was not good enough. So he came up with an inhomogeneous physical vacuum. And what he had was distinct boundary, more or less, whenever you had an anomaly. And when you were inside that enclosure, you had a different gravitic, electric, and magnetic field than outside. So you had this boundary. Now, he came up with a index of refraction, like you show. And from what I could tell, Popp went further by deriving a partial differential equation.
Yep.
Now, you mentioned that you went further than he did. I was curious if you looked at it in terms of coming up with a more advanced partial differential equation or more realistic solutions to that equation.
Well, to my knowledge, what Hal Puthoff came up with was a Lagrangian density for the field. And that's the only partial differential equation I'm aware of. And my understanding was that he got that from Dickey and from, I think it was a 1957 paper from Dickey about this type of scalar gravity model. And Hal came up with a Lagrangian density and modified it and got his own exponential solution. And then in around, I guess it was 2003 or 2004, a friend of mine who I used to know online, Joe Depp, wrote a couple of papers where he showed that there was an inconsistency in Hal's Lagrangian density that showed where it was an inconsistent, because if you're going to always say that the speed of light is c over k, then in the leading constant, c to the fourth should be over k to the fourth, and Hal had c to the fourth over k squared. And when Joe put in c to the fourth over k to the fourth and solved for the equations of motion, he got Schwarzschild's solution for the radial equation, not an exponential solution. And I showed that essentially that whole Lagrangian density breaks down into the Laplacian del squared times 1 over the refractive index. And you just do that and you'll get Schwarzschild's solution.
Well, that's interesting. What I'm kind of curious is, did he have a look at any sort of experimental validation of that approach?
He, in his first paper on it, the polarizable vacuum approach to general relativity, he goes through all of the tests of general relativity and shows that his approach fits the data. So he literally calculates out the perihelion of Mercury using his equation and his solution, and does this for time dilation, length contraction, and even later published a paper on the Levi-Civita effect. So yeah, he's done a lot of, he hasn't done the experiments, he's done the calculations that justify his solution fits the data from those experiments.
Well, I'm just kind of curious if you went use an extension of using experimental evaluation somewhere that was outside of the realm. And the other thing is, I was just kind of curious what would happen if you had a singularity. Now, if you say his problem was different because of that, not getting the other recognition, I'm curious what would happen if you hit a singularity.
I'm not sure what you mean by hit a singularity.
Let's say you have a nuclear explosion. You could look at that as a singularity. Let's say you have a propulsive device and something great happens when you have a singularity there, then you want to maintain that singularity. So that's the whole thing I'm thinking about.
I don't know, because I in my model, and I'm not sure if I buy this or not, but since I'm talking about matter, not space-time curvature, what I get from that damping factor, the damping ratio, is that if the damping ratio goes to 1, all motion stops. It's frozen. So
Yeah.
it's like at the event horizon of a black hole, there's nothing beyond that. It's stopped right there. It can't go any further because it's critically damped. Or I should say way over damped is what I should say.
Yeah.
It's damped to the point of no motion at all.
Okay. Thank you.
Okay, thank you again. Jeremy, do you have any questions from the YouTube Live that have come in?
Yes, I do. I have a question here from Quantum Mac. How does one measure the increase in the diameter of the point cloud of an electron?
You can't, not yet, but
Yeah, we can't.
You can measure the electron cloud on an atom, And this has been done recently. They showed an experiment. I saw it on one paper or another, one site or another. I saw it was a picture of the atom and with all the probability clouds there, but it didn't show any spacing. Now, going back 2015, 2014, Dr. Sonny White at NASA and Paul March did some modeling on COMSOL, and they modeled atoms in different vacuum environments and showed that they went, if you had an anti-gravity field or a warp drive propulsion, that these atoms would in fact expand. And so their data from the simulation shows it's possible. But other than that, I don't know of any way to do that. It's easier to measure time dilation because you can measure frequencies very, very accurately using spectroscopes.
And then I had another question about what about using muons instead of the electrons, because they're very similar, but they have a little bit of a higher punch, of course.
Same thing. I mean, it would work. It applies to any fermion.
Right. Any more questions from the live chat? Please put them in all caps. And thank you very much for your time today.
Okay, yeah, and thank you again, Jeremy. And then let me see, Paul had another question. So
yeah, Todd, at one of the STAFE conferences, you presented a paper for a propulsor using 4 antennas.
Yeah,
it looked very promising. Whatever happened to that?
In terms of what I proposed as a design, I went through it and essentially found where it can't exceed the speed of light. And essentially what it comes out to be is a photon rocket, which is designed as a unidirectional antenna. So it's basically broadcasting electromagnetic waves in one direction and moving in the other direction, but can never exceed, the thrust of the photon rocket.
I'm sorry to hear about that because it sounded pretty good and it's pretty simple concept.
Now the equation I got there in that paper from 2003, I think it was, warp drive propulsion within Maxwell's equations. That paper, I derived a scalar potential field that was a solution to this electromagnetic version of Cubier's metric. And in that, it's very similar to what I'm talking about here. It's a charge to mass ratio where Q is the charge on the entire ship and M is the mass to be transported. And then you have a scalar field potential that causes transverse oscillations, which could be thought of as these Larmor precessions that would then propel the craft forward. So I wasn't that far off, You're
not saying a pilot inside the spacecraft's got to bounce back and forth to get it going, right?
Yeah, well, we'll see. But the equation is there, and it amazes me that what I've got now takes me all the way back to there and says, oh, I had the same thing then. I had the charge to mass ratio multiplied by a scalar field, and I got propulsion from it. And here I'm just taking it to the quantum mechanic level instead of the electromagnetic Lagrangian density level.
We only learn from the past.
Okay. Moving forward, I like that. Anyway, I hope to have some experimental results soon. I do post my videos that I get on my YouTube channel, which is Warp Drive Tech. And Tim's welcome, and so is Mark welcome to post any of this on theirs as well.
Yeah, I would say send that over. Gary sent me his material earlier. Just send me any links that you want. I will add all of these in.
Cool.
Yeah. Well, so I think if we're all set, if we don't have any other questions, again, Todd, let me unmute everybody. We should probably figure out a better way to do this, but let me unmute everybody and give you an enormous applause. Thank you, sir.
A lot of fun. Thank you.
Thank you again.
Oh, man.
Okay, so let me put it on gallery view. And actually, let me go to Mark. I think, Mark, you had a lab update, right?
Working on it right now. Actually. We're working on it right now. Can you hear me?
If Mark's not there right now, we also had a question about the
Okay.
static. What do you call? He wants because Kazadin is asking to please elaborate more on the magnetic scalar potential.
Oh, we have more questions for Todd. Okay. Well,
Or,
yeah, if
or
we can-
anyone in the audience who can talk more about and explain what magnetic scalar potential is a little bit better.
Yeah, and that's
Could they mean gravitomagnetic scalar potential?
Todd, I think you're muted still, sir.
I said the magnetic scalar potential, it's as Richard talked about it last week. Essentially, you get a magnetic scalar field when instead of taking the curl of the magnetic vector potential, you're taking the divergence of the magnetic vector potential. And in the Lorentz gauge, they set that equal to 0. But in I think I got it backwards. The Coulomb gauge, they set that equal to 0. In the Lorentz gauge, you end up with the divergence is equal to the time rate of change in the electric potential. So the divergence of the magnetic potential is equal to the time rate of change in the electric potential. But that divergence of the magnetic vector potential is scalar magnetic flux, basically.
Wonderful. Thank you.